Hello, everyone. My name is Chong. This is a joint work with Professor Lalita Shankar. We are from Arizona State University. And the main focus of research is on pricing mechanisms for privacy-sensitive electricity consumers with access to alternative energy sources. Access to alternative energy sources enables energy cost reduction as well as privacy protection from the for the electricity consumers. However, this causes another problem because from the grid operation point of view, the change of load profile can cause serious operation problems since the the utility company wants or the energy provider wants to each household to consume certain amount of energy from the grid directly. So in this case, the electricity provider might need to offer incentives for users to consume a desired amount from the power grid for a stable and reliable grid operation. So basically, this work tries to study the trade-offs between privacy and the stable and reliable operation of the grid. And first, we want to study a model which captures the trade-off between privacy and utility for consumers. And then we want to design, from the perspective of the utility point of view, we want to design an incentive mechanism for consumers to share, to consume certain amount of energy from the grid. And then in this particular mechanism we design, we want to analyze the equilibrium behavior of the consumer and the electricity provider. So the model is denoted by this part, and we assume a distribution system with one utility and several households. And we assume that there is an elastic net demand of energy from each household, denoted by DIT. And by coordination of alternative energy sources, for example, batteries and PVs, it only consumes a proportion of energy of the net demand. And then from the electricity provider's perspective, it wants to incentivize consumers to consume certain energy from the grid. So basically, we model that by the incentive price beta, and it desires consumers in total to consume XT amount of energy from the grid. And the price model is given by here. Basically, what it says is if you're approaching the desired amount of energy by deviate from your privacy preserving consumption, I'm gonna reward you with a price beta. But if you deliberately not adhering to that, I'm gonna punish you with a negative beta. And the total payment to the consumers are given by this payment function over here, which basically is the sum of all the payment to each individual households, and the net profit function is given here. And the objective of the consumer is trying to maximize this compensation from the grid while remain their privacy to be under certain, to have certain level of privacy. And the objective of the energy provider is trying to maximize its net profit for offering incentives. So basically, we model this problem as a non-cooperative game, and the set of players is given by the households and the electricity provider, and the set of strategies given by the proportion they want to share with to consume directly from the grid, and the incentive price given by the electricity provider. And so, by the assumption of our previous model, this game consumer and energy supplier game satisfies an n-person concave game, so we can show the existence of the natural equilibrium. It's given by the work done by Rosen. And since we have proved that there exists a natural equilibrium for this type of game, so basically we want to find it. So but basically what we do is we want to compute the natural equilibrium from this setting, and assume that if the players have all complete information about this game, they can compute that by hand. But in this case, it is not, because each household only has its local information, which means the alpha IT and the beta T, which is the electricity incentive price. So we want to come up with a distributed algorithm to compute the Nash equilibrium. Basically, what it does is trying to use iterative update by using best response dynamics. And for simulation, we pick a generic function which is given by this two, and this is the net profit function, and this is the price constraint function given by in the objective of the consumers. And as we can see that the distributed algorithm converges to the Nash equilibrium in approximately 10 iterations. And this pricing mechanism helps to reduce energy imbalances for the system, as well as increasing the net profit and rewards for both consumers and the energy provider. So for future work, we are trying to develop a dynamic model the dynamic game model to study the interaction between the households and the electricity provider in a certain time domain, and we want to test this kind of pricing mechanisms on real power systems. Thank you.